We've always been told gravity is this fundamental force, right? Like this cosmic puppeteer pulling all the strings in the universe. But what if that's not the whole story? What if gravity isn't fundamental at all? What if it's more like a ghost, a shadow that's being cast by something way, way deeper?
Yeah, just asking that question, it shakes up one of the biggest assumptions we have in physics. The idea here is that gravity isn't some master force running the show. Instead, it might just be an illusion. Kind of like an echo, one that's bubbling up from the super weird, microscopic world of quantum mechanics.
So why are we even asking this? Well, it's because there's this massive problem, a real headache, right at the heart of modern physics. See, we've got these two amazing theories that, on their own, describe our universe beautifully, but they absolutely refuse to play nice with each other. It's like we have two totally different rule books for how reality works. On one hand, you've got Einstein's general relativity. It paints this picture of the big stuff, planets, galaxies, as existing in a smooth, continuous fabric of space-time. Think of a flowing river. But then you zoom all the way into the tiny stuff and you hit quantum mechanics. And it says, nope, reality is pixelated. It's jumpy. It's made of these little discrete packets of energy, more like a pointillist painting made of individual dots. And here's the kicker. Those two descriptions just don't work together. They're completely incompatible. I mean, how can you have a smooth, flowing river that's actually made of disconnected dots? You can't. Something's got to give. Okay, so this is where a fascinating new theory called CRET comes in. It proposes a pretty wild solution. It says, what if space-time isn't the fundamental thing we thought it was? What if instead it's something that's woven from the most basic ingredient you can possibly imagine, pure quantum information? Let's stick with that weaving analogy because it really helps. Think of it like this. Down at the tiniest micro level, you have the threads themselves. In physics, we call these qubits. They're the fundamental bits of quantum information. Now, at the middle level, the meso level, what weaves those threads together? That's quantum entanglement. It's the pattern of the weave. And then when you zoom all the way out to the macro level, what do you see? You see the finished product, a dense, tangled, but ultimately smooth-looking fabric. And that is what we experience as space-time. The physicist Mark van Ramsdonk put it so perfectly. He said, it's as if entanglement glues space together. And you really got to let that sink in. The idea isn't just that things in space are entangled with each other. No, it's so much more profound. The idea is that the entanglement is the space. The connection, the glue itself, creates the distance. It's literally the glue holding our reality together. Okay, but hold on. If space-time is just this delicate, flimsy weave of quantum threads, how does it end up looking so stable and solid and, classical? How does it become the world we actually live in? Well, the secret seems to be in this amazing feedback loop. It's like a constant conversation happening between the super small and the super large. It works kind of like a two-stroke engine. First, you have what's called upward amplification. This is where all those tiny entangled quantum threads build up from the bottom up to create the large-scale fabric of space-time. But then, and this is the crucial part, downward selection kicks in. The overall shape of that big fabric, the geometry, it actually feeds information back down. It sets the rules for the little threads, deciding which connections are allowed and which aren't. This whole process stabilizes everything. It's this incredible, self-sustaining cosmic loop. So what's the magic ingredient here? It all comes down to a tipping point. Think about the strength of that feedback loop, the combined power of the upward and downward information flow. We call this the total gain. And when that gain hits a value of 1 or more, bam, something incredible happens. The whole system just snaps into place. It locks into a stable resonance. All that chaotic, disconnected quantum fuzz suddenly crystallizes. It transforms into the smooth, classical, predictable spacetime that Einstein's equations describe so well. All right, so we've built this picture of spacetime from the ground up. But what about gravity? Where does it fit into all this? Well, If this model is right, then we've been thinking about gravity all wrong. It's not some external force that's pulling on the fabric of spacetime. No, gravity is an inherent property of the fabric itself. This leads us to a really cool idea called an entropic force. Now, don't let the name scare you. It's not a fundamental push or a pull like magnetism. It's a force that just emerges from a system's natural desire to get messier, to maximize its randomness or entropy. The fabric analogy works perfectly here. Imagine you have a snag or a wrinkle in a bedsheet. The tension you feel as you pull it smooth, that's an entropic force. The sheet isn't trying to be smooth. It's just settling into its most statistically likely, most random state. And right here, this is the big aha moment. Get this. In this model, mass, the very thing we thought was like a bowling ball bending the rubber sheet of spacetime, it isn't an object on the fabric at all. Mass is a flaw in the fabric. It's a spot where the weave is weaker, where the threads are less connected. It's a region with less entanglement. It's a snag, a defect in the quantum weave itself. So how does a flaw create a pull? How does this actually become gravity? Okay, here's how it works. You introduce some matter or energy into a region. What does it do? It locally reduces the entanglement. It creates that snag in the weave. Now, the rest of the fabric, the surrounding spacetime, it doesn't like this flaw. Remember, it's always trying to maximize its entropy, to smooth itself out. So it tries to fix the snag. And the tension that's created in that process, the pull towards the flaw as the fabric tries to heal itself, that pull is what we feel as gravity. I mean, this is a truly wild, almost poetic picture of reality, isn't it? But is it just a nice story, or is it actual real science? Well, the line between philosophy and science is testability. Can we actually test this idea? And the answer is yes. This model makes some very specific and very testable predictions. And we're not just talking about thought experiments here. These ideas lead to real-world predictions we can check in a lab. For instance, this theory says that if gravity comes from entanglement, then gravity itself must be able to create entanglement. So, if you put two tiny masses near each other, their own gravity should be able to entangle them. Believe it or not, there are tabletop experiments being built right now to test that exact thing. And if they succeed, wow, that would be huge. It'd be powerful, powerful evidence that yes, space-time and gravity are fundamentally quantum. And just as important for any good scientific theory, it tells us exactly what would prove it wrong. For example, if we ever found two objects attracting each other, but we couldn't find any corresponding decrease in entanglement between them, well, the theory would be in big trouble. Or if those experiments I just mentioned fail, if we prove that gravity cannot entangle objects, that would break that whole downward feedback loop. This is what we call falsifiability, and it's what makes this a real solid scientific hypothesis, not just some fun idea. So this all leaves us with one final, absolutely mind-bending thought to chew on. If this picture of the universe is even close to correct, it means that everything, gravity, the geometry of space, the very stage on which reality plays out, it's all just an emergent property. It bubbles up from quantum information. Think about that. The cosmos isn't a box that contains information. The cosmos is the information. And that, well, that's a thought that'll stick with you.